My name is Alex Steele, and today I'll be talking about native extension modules for Python. So this talk will be a bit less concrete than some of the others today. There won't be any live coding or snippets that you can paste into the command line, but I'm hoping that we can go over some general principles that'll be of use to anyone who's considering writing a native extension module for a personal project or at work. We'll go over some brief background over what native extension modules are and how they work, then how you might decide whether or not you need one, performance considerations when working across the Python foreign function interface, and then architecture patterns that are often useful when writing native extension modules. Okay, so some quick background. A native extension module is just any Python module that's written in a language that compiles to native code and it exposes new built-in objects to the interpreter. Built-in's in quotes because it's not technically built into Python, but it's viewed quite similarly by whatever interpreter you're using. So this is the API that is used on the back end of all the common scientific Python and numerical computing libraries that you're familiar with, so NumPy, SciPy, PyTorch, Pydantic, etc. They all use native extensions for some of their functionality. And the classic way to make an extension module is using the Python API for C, but these days several high-level frameworks now exist. So there's Boost.Python and PyBind 11 for C++. I've used PyBind 11 a bit. Boost.Python is a bit older, but plenty of people still use it. And the new kid on the block is Py03 for Rust, which is used by Polars and Pydantic, I believe. I'm not going to get super into the details about these frameworks, both because I don't have the time and because they're both changing at a decent clip. Like Py03 recently rewrote their entire memory model earlier this year, so anything I say will probably be out of date by the time you actually find yourself using them. So when should you use a native extension module? So there's plenty of advantages to calling native code from Python. So if you have some really good image processing framework that your company has written in C++ and you don't want to re-implement that exact same thing in Python, you can just write bindings for it and avoid reinventing the wheel that way. You can keep those performance gains from C++ and not have to worry about hot paths in your code going through Python and slowing things down. And it opens up new ways you can use Python. So you can interact directly with hardware and low-level systems. If you have some sort of hardware tester of some sort, if you've got any sort of embedded system, you can interact with that at the C ABI level and then call into that through your Python interface. But there are some trade-offs here, and I'm not just saying that because it's rude to come to a Python conference and say you should be using Rust instead. As soon as you add a second language, system complexity increases quite drastically. So you now have to deal with whole new layers of abstraction where Python calls go down to a different language, which might go down to another language. Like if you look at NumPy's source code, it goes from Python to C, and then there's some Fortran in there, and it's very difficult to trace back to what's causing a bug if you're developing that library. Portability can also be a challenge there. So as soon as you start involving native code, you need to be building wheels for all operating systems and architectures and Python versions that you're targeting, or you're going to need to have to rely on your users having a compiler that supports whatever languages you're using. And lastly, tooling is just annoying whenever you have a native extension. So that's not just like now you need to have a C auto formatter and a C linter as well, but if you have an IDE and you control click or command click on some function call, that's either not going to take you anywhere or it's going to take you to a Python interface file which just has stubs. It can be a lot more difficult to work in these sorts of mixed code bases. So the reason I'm saying all this is that if you're considering using a native extension, then make sure that there's value on both sides. Why do you need Python and C++? If it's just a performance question, then it's probably easier to just write the app in straight C++ and not have to worry about the FFI, because crossing the FFI and doing that safely and efficiently can often be quite a bit more complicated than just writing it the right way in C++ to begin with. So I mentioned performance there. The key consideration is that crossing the foreign function interface is very expensive. No matter what API you're using, you're going to need to convert back and forth between Python types and native types, and that will slow down your code and is running counter to what you're trying to do oftentimes. So don't feel obliged to copy whatever API you're using in C or Rust or C++. Use something that makes sense for Python and makes sense for minimizing calls across the FFI. So you can use context managers, you can batch operations where instead of calling into some foreign function interface function in a hot loop, you move that loop into the native code itself. The global interpreter lock is easier to work around in native code, particularly once you're not dealing with any Python objects anymore, so you can parallelize if it makes sense. If you're using Rust, it can be as simple as changing one line. And as always, write benchmarks and profile them to find any hot points in your code. PySpy is a really good sampling profiler that I've used that supports native extensions, so you can see all the way up from your Python main function down to system calls that your native extension is using. Okay, I got 3 minutes left. Some other considerations are more architectural. Whenever you're dealing with the Python API, you should be thinking of that as a separate concern from the business logic of whatever your library is doing. So if I'm interacting with like some low-level robotic simulator that I wrote in C++, I don't want the Python API to be permeating throughout that simulator code base. Something I often find useful here is just making them completely separate packages or completely separate crates in Rust. And that way you can just pull in your original code as a dependency and not have to worry about bringing in Python considerations as a cross-cutting concern in your library. So like I mentioned earlier, you should be writing your API with Python users in mind. The whole reason many of us like to use Python is its simplicity and accessibility, especially for people from a more non-technical background or people who might have a technical background but aren't software engineers and they're working as domain experts. So if you're trying to avoid having to teach a bunch of validation engineers C++, then don't make them write C++ in Python. Okay, so some quick takeaways. Only use a native extension if you're getting value from both sides of the FFI. Both Python and the natively compiled language should be providing value to you. FFI calls are expensive, so minimize them if possible. And you're still writing a Python module, so it should be as accessible as possible to other Python users. Okay, that's all I had. We have about 80 seconds if anyone has any quick questions.
Any questions? Okay.
Hi. Can you give an example of where this has been beneficial for you?
Begging your pardon?
Can you give an example of a native application, native extension you had to write in a practical scenario?
Yeah, so when I was in university, I was responsible for writing some code similarity detection tools, and the hot loop involved lots of Levenshtein distance calculations, which I was able to move into a Rust crate and drastically speed up runtimes, and was able to process tens of thousands of files in quite reasonable times given the hardware available.
Hi, I have a question. My name is Annie Salazar. I have a question for you. What are your current projects or plans for the future that you can tell us about, what the possibilities of Python and C++ or whatever projects you'd like to have or?
That's a bit of a longer question. I can follow up outside if you'd like.
Let's thank Alex again. We need to move